So next we're going to discuss matrix inverses. So here's the idea behind matrix inverses. We'll start with a square matrix because this definition is only going to apply to square matrices. So let's say we've got some n by n matrix A. Well, here's what it means to be invertible. So A is invertible. In other words, it's possible to invert it, whatever, and that's what we're going to give meaning to now. If the following happens, if there exists an n by n matrix B, so another square matrix of the same size as A, such that the following holds. So we have two equations that we're going to require to be true. If you multiply this matrix A on the right by this other matrix B, you get the identity. And if you perform the same product, but you have the factors trade places so that B is the factor on the left and then A is the factor on the right, you also get the identity matrix. So if these two equations are true, and A is a square matrix and B is a square matrix of the same size, then we say that A is invertible. And in this case, we actually say a little bit more. So if this happens, we say the following. We say that B is the inverse of A, and we write A inverse like that is equal to B. So what I've done is I've just written the matrix A and then with a superscript, kind of like where I would write an exponent if we could write exponents on matrices. It turns out we can. We haven't defined them yet, but we will soon enough. But this is not an exponent, it just looks like it. It's just a superscript, and you write a -1. So if I write A with a superscript of -1, that's the notation that I'll use for the inverse of A. And it's going to be automatically equal to whatever matrix B satisfies both of these equations. Right? If I multiply A on the right by B, or if I multiply A on the left by B, I get the identity in both cases. And notice that I didn't specify the dimensions of the identity matrix here. And I did mention that on the previous page. We said that if the context makes the dimensions clear, we will omit the subscript sometimes. And this is another one of those cases. Where the dimensions are forced by the context. Because if A is an n by n matrix and B was also an n by n matrix, if you multiply two n by n matrices, the result is going to be again an n by n matrix. And same with over here. I had an n by n times an n by n. This is going to be an n by n matrix. So I didn't specify the dimensions of the identity matrix, but if I did, I would use an n here as a subscript here and here. But not doing that is okay since the dimensions are forced by the context. Let's look at an example. One comment, which this example will just reinforce, is that the letter B was used because you need something. You need to give the inverse B of the matrix A a name so that you can actually describe what it means to be the inverse of the matrix A. But once you've set that up and you've made that clear, then you can use the notation A inverse instead. But really, we can't use the notation A inverse to say what an inverse means because we haven't said what it means yet at that point. It would be circular. So the lifetime or the usefulness of the letter B kind of ends with this sentence. And once we have said exactly what it means to be an inverse, we can just use this notation for an inverse instead. So this example won't use the letter B at all, just to give you an idea of what that means. So let's write down a matrix. Here's the 2 by 2 matrix. 2, -5, -1, and 3. And I'm going to claim to you that A inverse, so I'm not going to use the letter B, I'm just going to write A inverse, is equal to this matrix, 3, 5, 1, and 2. So how on earth would you check that this is the case? How do you know if this is true or not? Imagine you were trying to find an inverse of the matrix A, and somebody comes in, they come bursting in the door, and they say, hey, I can tell you the inverse of A. It's given by this 2 by 2 matrix over here. How do you know if they're telling the truth? Well, you'd have to go back up to what it means to be an inverse, and you'd have to verify that these two equations are true, where instead of B, we would use this matrix down here. So if I take this matrix and I plug it in for B in both of these equations and they work, I get the identity for both products, well then that means that this is true and that this is the inverse of A. So let's do that, or let's check that. So we'll start with the matrix A, 2, -5, -1, and 3, and we'll multiply it on the right by this other matrix, which I'm claiming is A inverse on the right. So let's work this product out. It's a 2 by 2 multiplied by another 2 by 2, so the dimensions of the result will be 2 by 2 as well. Let's work out the entries. 2 times 3, which is 6, -5 times 1, which is -5, so we've got 6 minus 5, which is 1 for the entry in the first row, first column. For the second entry in that column, let's go -1 times 3 and 3 times 1. That's going to be -3 plus 3, which is 0. What about this entry up here? This is first row, second column. So first row, second column. 2 times 5, -5 times 2, that's 10 minus 10. And then for our last row, we got -1 times 5 and 3 times 2, that's -5 plus 6, which is 1. So that's the identity matrix, right? So that's good. That's half the story. Let's check that the product works in the other way as well. So 3, 5, 1, 2. So I'm putting this factor on the left now, and then I'll put the A as the factor on the right. Okay, so let's do the product in that order. And we are expecting to get the same thing, but let's check. 3 times 2, 5 times -1, that's 6 minus 5. 1 times 2, 2 times -1, that's 2 minus 2. 3 times -5 and 5 times 3, so that's -15 plus 15. And then we've got 1 times -5 and 2 times 3, that's -5 plus 6, which is 1. So that does it. These are the properties that need to be checked. So these, I'll say these equations, are what needed to be checked. So this one here and this one here. And just a reminder, in case you're wondering, why would we need to check the multiplication in the other way? Wouldn't it be automatic that if we multiply them, these two matrices, we multiply and get the identity this way? Isn't it automatic that if we flip the order, we get the same thing? And the answer is no. Remember on the very first page, we made a cautionary note in general against making that assumption. In general, if you take two matrices and multiply them in either order, you may not get the same thing. And this is an example of two by two matrices that, if depending on which order you multiply them in, you get completely different results. So at this stage, for checking inverses, we don't have any technology for this yet, but we have no choice but to check them in both directions. However, since it worked in both directions, we can say confidently that this is the inverse of A. And actually, I just used the word the and said the inverse of A. How do we know that there can't be more than one inverse, right? How do you know that there couldn't be several matrices that satisfy the role of B in both of these equations? We haven't ruled that out, but it turns out it never happens. If there's only ever going to be at most one matrix that satisfies both of these conditions, and that's what we'll verify now. So here's the note. Inverses are unique. And what does that mean exactly? So if we have the following, so let's say I had some matrix B which satisfies both of these equations, then I'd have AB is the identity, and I'd also have B times A is equal to the identity. These two conditions together imply, based on this definition that we wrote down at the beginning of this page, that B is the inverse of A, or at least is an inverse of A, although we did use the word the here, which implies that there's only one. But let's justify that now. What if I had the matrix B that satisfied both of these equations and also some other matrix? We got to give it a different name, so how about C? Such that AC is the identity and also CA is the identity. Let's say we had all 4 of those be true. Well, my claim is to you, then B and C are already the same matrix. Notice that these 2 equations are exactly what you would get if you just rewrote these ones, but you replaced the letter B with some other letter C, and I'm using C in this case, so it's some other matrix. So I'm claiming to you that this means that B and C are actually the same matrix if all 4 of these equations are true. So let's look at why that's the case. Start with the matrix B. You can always write B is equal to B times the identity. Remember, that was key property of the identity. If you take any matrix A and you multiply it by the identity on either the right or the left, you just get the matrix A back again. So that's going to also hold for this matrix B. And for I, the identity, we've actually got 4 different representations of the identity matrix as products. So we can use any ones we like to replace this I with a product. And I'm going to use this one here. I'm going to replace the identity matrix with the product of A and C. Right, so far so good. I haven't broken any rules. I've just used different representations for the same matrix. Now, remember the associative property of multiplication? On the very first page, it was property 3. Right, if I have 3 matrices multiplied, I can pick any 2 to multiply first, as long as I don't change the order that they're written. So if I have A, B, and C, I can multiply the second 2 factors first, or I can multiply the first 2 factors first. And either way, this property says they're going to give me the same result. So let's do a bracket shift here. I'll rewrite this as BA times the matrix C. And you might be able to see where I'm going now with this, because this BA, well, according to this rule, it's also the identity. So this is actually just going to be the identity matrix times C, and then, well, the identity matrix times C is actually just C. So we've created this chain of equalities, right? B is equal to B times the identity. B times the identity is equal to this expression, and this expression is equal to this expression, and so on. What we've done is we've created an equation link between B and C, right? Or a link of equalities, a chain of equalities, however you want to call it. We've shown that B is equal to C now. So this is what it means when I say that inverses are unique. If you had 2 potentially different matrices that satisfied the same job of an inverse, in other words, they satisfy both of these equations, then it turns out that all you've done is just give them different labels, but they're actually, in fact, the same matrix. That's what this shows. Okay, so, but that doesn't really leave you satisfied, right? Because where did this matrix come from, right? I just gave you this out of nowhere, and then we, as an example of showing how inverses work, we checked that these 2 equations were true. But what if you didn't have this? Then what would you do? And that's the question we're going to answer next, at least for the case of a 2 by 2 matrix. So here is a theorem. So we'll start with writing down a general 2 by 2 matrix. Okay, so I've just written A, B, C, and D to represent its 4 entries. Now there's 2 claims to this theorem. The first claim is as follows. If I take the product of A and D, and then I subtract the product of B and C, so this product minus this product, if it's not equal to 0, whatever it is, as long as it's not equal to 0, it turns out that A is invertible. So that at least tells you something. That means it does have an inverse, but it doesn't tell you what the inverse is. But fortunately, we also have that information. We can say the following. We can say that A inverse is equal to 1 over AD minus BC, which we already know that's not 0 by assumption here in this, the way this sentence was started. So this is a well-defined fraction since the denominator is not 0. But A inverse is going to be given by this scalar times the matrix, which you can obtain them from the entries of A as follows. First of all, just switch the A and the D, have them trade places. And then for the B and the C, just introduce negative signs. We've got that representation for A inverse. So that's what the first statement of this theorem. So if you form the product of A and D and you subtract the product of B and C, and you subtract them, you're going to get, and if you get something that's not 0, then that tells you that the matrix A is invertible, and here's the formula for its inverse. So it's quite powerful. It tells you the whole story. And the second claim, you might be able to guess what it's going to be regarding, but, well, this might be 0, right? That's one way that this part could fail. So, no, the only way that this could fail. But what if AD minus BC is equal to 0? Well, then we certainly can't compute this, right? Because I can't go 1 divided by 0. You can't divide by 0. So this formula won't work for A inverse. But it turns out not only will this formula not work, but that A just doesn't have an inverse. So if this is equal to 0, then A is not invertible. So that's the other claim of the theorem. So what I'm going to do is we're going to prove together, we're going to prove the first claim, at least. We won't actually prove the second one just yet. We can come back to the second statement later. But for now, I'll just state it as truth. But we'll prove the first one carefully. So how would you do that? How would you check that if A is given by these 4 entries, this 2 by 2 matrix, and if AD minus BC is not equal to 0, then A is invertible, and this is its inverse? Well, let's just check. Right, let's just take this matrix and multiply it by A on either side and make sure we get the identity back. And if that works, then that's enough to prove the first statement. So let's start by taking the matrix A and multiplying it on the right by this matrix here. Got 1 over AD minus BC, and then times this matrix here. So D, negative B, negative C, and A. So that is the product. Now let's work it out and make sure we get the identity. Well, this looks like there's a lot here, right? You've got a matrix, and then in this pair of brackets, you've got a matrix times a scalar. That actually matches the form of property 13. We actually have something that looks like this, right? We've got a matrix multiplied by another matrix, which is obtained by taking a scalar and multiplying it onto a matrix. That's really what we have in brackets. But property 13 says, well, we can pull the scalar alpha right out in front and then just multiply the 2 matrices directly. So I'm going to use the equivalence of this expression and this expression now to just pull, this is like your alpha. So pull that out in front. So you've got 1 over AD minus BC. And then the 2 matrices we're multiplying, I'll just write them directly side by side, and now we can perform that multiplication. So just the scalar, leave that scalar alone for now. So let's multiply these 2 by 2 matrices. So the product of 2 by 2 matrices is going to, again, be a 2 by 2 matrix. So let's work out the entry in the first row, first column. So we're going to have A times D and B times negative C. So that's going to be AD minus BC. If we don't know what the letters actually are as numbers, that's the best we can do. We just have to write them down symbolically. What about this entry? C times D and D times negative C. That's going to be C times D minus DC. We'll just write it down. The next entry up here, A times negative B and B times A. So this is negative AB plus BA. And then the entry down here, we have C times negative B and D times A. So negative CB plus DA. Okay, great. Let's clean this up a little bit. If I just, well, leave this alone. 1 over AD minus BC. Now what happens here? AD minus BC, that can't do much with that. CD minus DC, well, order doesn't matter for multiplication of numbers, right? So CD minus DC, this is just going to be 0. Same with negative AB plus BA, right? These are just negatives of each other, so those terms are going to cancel. And then last, down here we have negative CB plus DA. Well, if I just rewrite this a little differently, if I rewrite the DA term as AD, and then I rewrite the negative CB term as minus BC, and why am I doing that? Just to make it more evident that this quantity and this quantity is the same as this quantity. So if I had a 3 here and I multiply by 1 over 3, I'd just turn it into a 1. Same with down here. So what you're going to end up getting is the 2 by 2 matrix consisting of 1 along the main diagonal, 1's along the main diagonal, and 0's elsewhere. So this is the identity, right? That's the 2 by 2 identity matrix. So that is the end of checking that this statement is true, but we still should check the other one, right? So that's, I haven't got enough room on this page, so we don't quite have enough room to do it, but we can do that on the next page. But this needs to be checked as well.